Welcome to the Chemistry 450 Atomic and Molecular Clusters Key Concepts video series. In this video, I will discuss free electron theory. For our purposes, we will consider free electron theory in the context of metallic systems where valence electrons are uniformly distributed amongst the ion cores to form a free electron gas. This gas is confined to the volume of the metal particle. From the perspective of the nth electron, the n-1 other valence electrons effectively shield the n ion cores. Thus, the nth electron occupies a region of constant electrostatic potential within the metal nanoparticle. This construct allows us to treat the nth electron as a particle in a box. For a one-dimensional particle in a box, level energies depend on the mass of the particle, in our case an electron, the length of the box, and the quantum number n. For those who would like further discussion about the one-dimensional particle in a box problem, I would direct you to the wave mechanics video in my spectroscopy masterclass series and to the particle in a box video in the mini tutorials in spectroscopy series. Since clusters rarely adopt linear geometries, we need to consider how structure is affected by higher dimensions. We find that a particle in a 2D rectangular box exhibits wave functions which are a product of sine functions describing behavior in the x and y directions, and energies which are a sum of the x and y energies. Here we have quantum numbers for the x and y dimensions, and lengths in the x and y directions. Unsurprisingly, we arrive at a similar product of sine functions and sum of energies description for particles in a cuboidal 3D box. It is important to note at this point that most clusters for which we might use free electron theory don't actually adopt cuboidal geometries. We'll connect free electron theory with the spherical cluster approximation in due course. Nevertheless, it is useful to compare the predictions of free electron theory in one-dimensional, two-dimensional, and three-dimensional boxes, since this will reveal important insights as to how size and shape can affect electronic structure. For example, compare the electronic energy level structures of these three isomers of sodium-8, 1x8 linear, 2x4 rectangular planar, and 2x2x2 cubic. The density of electronic states is much higher for the linear isomer than for the planar isomer, which has a higher density of electronic states than the cubic structure. It is clear from this comparison that larger boxes yield more closely spaced electronic energy levels, and that increasing cluster symmetry increases level degeneracy. Note, however, that our energy level diagram does not tell us anything about the relative energies of these three isomers. We will discuss relative isomer energies in a future video. See you next time.